Hello, my name is Bada Mendoza. I'm currently a master's student at the University of Florida studying PFAS with Nicole and Yolan and under the direction of Dr. Townsend. We're currently looking at membrane treatment just because, as you can see from Yutao's presentation, it was very effective in removing PFAS as a treatment for landfill leachate. So reverse osmosis in itself has very high salt and ion rejection, but it does create a brine. And just to kind of conceptualize that, here's a little diagram that shows the feed solution and the permeate and the concentrate that's created from that, the concentrate being that brine and the permeate being that clean effluent. Unfortunately, it does require high pressures, upwards of 200 psi, and even more depending on the dimensions of your actual membrane and the volume that you're dealing with, and that does incur a high cost. It also is vulnerable to organic fouling from waters that are rich in natural organic matter, which is the case with landfill leachate since it is very turbid and very difficult water matrices. In the literature, there's not a lot out there that deals specifically with sequestering PFAS and landfill leachate. What does exist, there's a couple case studies, one specifically in China. On the upper left-hand or right-hand corner, you can see the specific sites that were tested, and it doesn't ever really specify the reverse osmosis by itself. There's usually some pre-treatment prior to the reverse osmosis, usually ultrafiltration or biological treatment, or something before it actually gets to the membrane, just because the membrane is so susceptible to fouling. Another case that you can see is on the bottom graph, and that's the Germany case by the famous Bush paper in 2010. On the right-hand side, you can see that biological treatment and nanofiltration, as well as activated carbon, rejects PFAS, but not as well as reverse osmosis. As you can see on the left, there's almost 0 to none leftover rejected PFAS in the treated waste stream or landfill leachate. According to these two papers and a couple other studies, there's widespread acknowledgement that there's high PFAS rejection, upwards of 99% for reverse osmosis, a little bit lower than that for nanofiltration, even though it's still highly effective. But there are several studies that do talk about reverse osmosis and nanofiltration for PFAS treatment on drinking water and artificial industrial waters. It has been identified by several other papers that more research needs to be done for long-term operating data at the pilot or full scale to validate practical viability. So in our case, we're interested in exploring the effects of low, medium, and high concentrations of PFAS and what this means with the membrane. We also want to look at different physical and chemical parameters and how that affects rejection rates, including total organic carbon, COD, BOD, pH, and how these different water matrices affect the membrane fouling. We're going to be able to look at 52 different PFAS constituents, including PFCAs, PFSAs, precursors, and we'll also be able to target those unknown PFAS constituents via full scan unique analysis, which is what Nicole mentioned earlier. So again, thank you so much for your time, and if you have any questions or comments, please feel free to reach out and let us know. Thank you.